When grounded neutral and grounding bus bars are connected to subpanel, it creates an electrical path between the grounded circuit conductors and the equipment grounding conductors. This can lead to a hazardous condition called a ground fault current path. When a fault occurs on a grounded circuit, such as a short circuit or an appliance malfunction, current can flow through the grounding conductors back to the main panel. However, if the grounded and grounding bars are connected in the subpanel, this current can also flow through the neutral conductors, which are intended to carry current under normal conditions. This excessive current can overload the neutral conductors, causing them to overheat and potentially start an electrical fire. If the grounded and grounding conductors are connected, a person touching a metal component of the subpanel or an electrical device connected to it could be exposed to dangerous electrical currents. This is because the metal component would become energized, creating an electrical shock hazard. Ground fault interrupters, or GFIs, are devices designed to protect against electrical shock hazards by detecting imbalances between the current flowing through the hot and neutral conductors and tripping if a fault is detected. If the grounded and grounding bars are connected, ground fault currents can flow through the neutral conductors, causing GFI to trip unnecessarily or even fail to trip when a fault actually occurs. By isolating the grounded and grounding bus bars in the subpanel, the electrical path for ground fault currents is restricted, preventing these hazardous conditions and ensuring the safe operation of the electrical system. To elaborate on the importance of proper grounding in electrical systems, consider the fundamental principles at play. Firstly, the grounding system is designed to provide a low impedance path for fault current to return to the source. This path is crucial for the operation of overcurrent protection devices like circuit breakers and fuses. When a fault occurs, a large current surge flows through the grounding system, causing the overcurrent device to trip and disconnect the circuit, thereby preventing damage to equipment and reducing the risk of electrical shock. Secondly, the separation of the grounded neutral and grounding conductors in the subpanel is essential to prevent circulating currents in the grounding system under normal operating conditions. When the neutral and ground are connected at multiple points, such as both at the main panel and the subpanel, a parallel path is created for neutral current. Some of the neutral current will flow through the grounding conductors back to the source. This can lead to several problems, including nuisance tripping of GFI, increased electromagnetic interference, and elevated voltage potential on grounding conductors. Thirdly, the National Electrical Code, or NEC, specifically addresses the proper grounding and bonding of electrical systems to ensure safety and compliance. NEC Section 250.24 A5 states that an equipment grounding conductor shall not be connected to the grounded conductor on the load side of the service disconnecting means, with certain exceptions. This requirement is in place to prevent the aforementioned issues associated with connecting the neutral and ground at multiple points. Fourthly, understanding the role of bonding in an electrical system is also crucial. Bonding refers to the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed on it. Bonding helps to minimize voltage differences between metallic parts, reducing the risk of electric shock. In a subpanel, the metal enclosure must be bonded to the grounding bus bar. Fifthly, when installing or inspecting electrical systems, it is important to verify the integrity of the grounding and bonding connections. This can be done using a multimeter or a ground impedance tester. A low impedance reading between the grounding bus bar and metal enclosures indicates a good bonding connection. High impedance readings may indicate loose connections or corrosion which can compromise the effectiveness of the grounding system. Sixthly, GFI operate by monitoring the current balance between the hot and neutral conductors. Under normal conditions, the current flowing through the hot conductor should be equal to the current flowing through the neutral conductor. If there is a difference of 5 mA or more, the GFI will trip, interrupting the circuit and preventing electrical shock. When the neutral and ground are connected in a subpanel, ground fault current can flow through the neutral conductor, reducing the sensitivity of the GFI and potentially preventing it from tripping in a timely manner. Seventhly, consider the impact of harmonics on neutral conductors. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear laws such as electronic devices and appliances. These harmonics can cause the neutral conductor to carry more current than it is designed for, leading to overheating and potential fire hazards. Properly separating the neutral and ground conductors helps to mitigate the effects of harmonics on the grounding system. Eighthly, surge protective devices, or SPDs, are often used to protect electrical equipment from voltage surges caused by lightning strikes or power grid disturbances. SPD work by diverting surge current to ground, thereby preventing it from damaging sensitive electronic components. A properly installed grounding system is essential for the effective operation of SPD. Ninthly, electrical inspectors play a vital role in ensuring the safety of electrical installations. During an inspection, they will verify that the grounding and bonding systems are installed in accordance with the NEC and other applicable standards. They will also look for any signs of damage or deterioration that could compromise the integrity of the electrical system. Tenthly, it is important to note that electrical codes and standards are constantly evolving to reflect new technologies and best practices. Staying up to date with the latest changes to the NEC and other relevant standards is essential for electricians, engineers, and other professionals involved in the design, installation, and maintenance of electrical systems.